Now we are going to see the application of CFT in octahedral complexes. Before going to in the octahedral complexes, first we must know how the metal is approached by ligand. The metal is approached by 6 ligands because we are going to discuss about octahedral complexes. Application of CFT in octahedral complexes. That means 6 ligands are going to approach the metal ion. 6 ligands are going to approach from corners of the x, y, z axis. If I am considering this as x axis, y axis and z axis. Corners of the x, y, z axis, these ligands will approach the metal ion. This is the first point in the this particular explanation. In this first point, all the ligands are approaching the metal ion from the corners of the x, y, z axis. Now, point number 2. Point number 2, it is very clear that when it is approaching, there are two ways. First point 1. In this 2, a subpoint is 1, and in this point, how the ligand is approaching the metal. The ligands are approaching the metal in a spherical way. Already we discussed from the postulates itself, during a spherical approach, the energy, the degenerate orbitals, that means the one we have which are having same energy will move to here. That means increasing energy. The energy will increase, and this level, at this level, will consider as energy is 0, and we will call it as barycenter. Right. First point A is over. Well, the ligands are approaching spherically. That means energy increased. Now, point number 2. Now, in this particular octahedral complexes, the ligand approaches the metal ion along the axis. Very important point to be noted. Along the axis. If along the axis, if ligand is approaching the metal ion, what happens? In this one, we already know that these are having dxy, dyz, dzx, dx square minus y square, dz square. Right? Of course, same. Among these three are the orbitals are present between the axis. These two orbitals which are having lobes along the axis. Very important point. These two along the axis, these through the axis, between the axis, through the or between the axis. So, here is the point. Now, the ligands are approaching the metal ion along the axis, and so what happens? I am going to continue this particular image from here, right? Once after it's reaching the barycenter, I am considering this as barycenter. Already energy raised. From this one, it will split into 2. How it will split? It will split into 2, in which it is approaching the metal ion along the axis. That means the energy bit dx square minus y square and dz square. This is called as easy. This easy symbol I'll explain you after within few minutes. Whereas here dxy, dyz, dzx. So, how this splitting happened? Because I already explained the ligand approaches the metal ion along the axis. That time what happens? Whichever lobes are present along the axis, that means dx square minus y square. Whoever lobes are between the axis, that is dxy, dyz, dzx. These three orbitals will experience less repulsion, whereas dx square minus y square will experience more repulsion. Very clear point. Why they are experiencing more repulsions? Because they are present along the axis. Why these are having experiencing less repulsions? Because they are present between the axis. This is the point to be noted very carefully, because the splitting all depends upon the shape of the orbitals. Now let us consider this as barycenter. This as barycenter, right? And here the splitting is going to be 0.4 delta naught, right? And this splitting is going to be 0.6 delta naught. What is 0.4 and 0.6? That means this is got the energy got reduced by 0.6 naught, and the energy got increased by 0.6 naught. Increased due to repulsions, and reduced also the splitting happened exactly from the axis. Barycenter is the one which is having zero energy, the above one is having high energy, the below one having low energy. And here these two or three orbitals we are going to call it as T to Z. This EZ and T to Z are called Mulliken symbols. This 2TZ and EZ are called as Mulliken symbols, in which E is indicating doubly generated, doubly means 2, whereas this T is indicating triply generated, triply degenerated, that means 3, and this G garred, that means that will come under symmetry point. Garred will come under symmetrical point. So this is the way that it will undergo splitting in this type of octahedral complex. Now this splitting, this splitting is going to be indicated with delta naught, where delta is indication of splitting and O is the indication of octahedral splitting, right? And moving on to the next point, that is the third point, right? So this splitting depends upon the nature of the ligand, or strength of the ligand. What it means? If the ligand is strong, then the splitting happens more. If the ligand is weak, then the splitting happens less. The splitting depends upon the nature or strength of the ligand, right? For example, if I am taking an example, I am going to take one example, FeCN6 2 plus X minus 6 plus 2. It's supposed to be plus 2, right? So that means it's minus 2. If I am taking FeCN6 minus 2 complex, in which metal is going to have plus 2 oxidation state. Metal is going to have plus 2 oxidation state. Apart from that, these cyanides, how many ligand molecules are there? 6 ligand molecules are there. In this this is going to be example of octahedral complex. Why? Because 6 ligands are there. This cyanide and is a strong ligand. How to know which is strong ligand, which is weak ligand? That is explained based on the spectrochemical series. In spectrochemical series, if you are considering, this cyanide is going to be strong ligand, and so when the ligand, when this type of strong ligands are approaching, when this type of strong ligands are approaching the metal ion, the splitting occurs more. If the splitting occurs more, that means delta naught will be more compared to pairing energy. What is pairing energy? The energy required to pair electron, that I am going to explain the next point. Here delta naught will be more than pairing energy whenever the ligands are strong. What is delta naught and pairing energy, and how this cyanide strong ligand will split, that I am going to explain now, right? I am going to take an example which I already told you, FeCN6 2 minus. In this one, the cyanide is strong ligand, strong ligand. and hence the splitting happens. This is barycenter in this way. Here it is going to be easy. Here it's going to be T2Z. So here the complex which I am going to take is FeCN6. Let me take one more example, that is FeH2O 6 2 plus. So why I am taking second example here? In this one the ligand is weak. Water is a weak ligand. So by comparing these two, we can understand the splitting very easily. So let me explain you the cyanide. When cyanide is there, the delta naught will be more compared to pairing energy. What it mean? Now let me write Fe plus 2 oxidation state here. Fe plus 2 means it's going to be which configuration? D6 configuration. D6 configuration means we have to fill 6 electrons in it. How many electrons? 6 electrons. 3d6, 4s2. Obviously, plus 2 will come into picture. This will go d6. How many electrons we have to fill? 1, 2, 3. Now, filling of these 3 electrons are somewhat okay. Now, fourth electron we are going to fill here or here. That depends upon the strength of the ligand. For example, as this ligand is a strong ligand, the distance between them will become more. That means delta naught will become more compared to pairing energy. What is pairing? The energy required to pair the electron. For example, if I am adding electron here, that is the pairing energy. So if I am adding electron here, that is pairing energy. That is less than this delta naught. Delta naught is more than pairing energy, and hence delta naught is more than pairing energy. As its splitting is more, we cannot the next electron cannot enter into this particular one, and this will undergo pairing, right? So this is the arrangement of electrons of the D6 in whenever the strong ligand is there. Now moving on to same way weak ligand. So I am going to take again barycenter here. Now when weak ligand is approaching, what happens? Again splitting happens. There is no difference between splitting, but the extent of splitting is matters. The extent of splitting depends upon strength of ligand. Here water is weak ligand, and so what happens? Now here also Fe is in plus 2 oxidation state, and here also electrons are 6 only. Now how I am going to do arrange these electrons here? 1, 2, 3, right? And in this case, as it is weak ligand, the delta naught is going to be less than pairing energy, right? And here what is going to happen? Here what is going to happen? The fourth electron is going to be filled here. Why? Because the which is weak ligand and the splitting is not bigger, and so the fourth electron can enter into the higher energy level. Fifth electron will enter here. Sixth electron will enter here. So this is the arrangement of D6 in presence of strong ligand and in presence of weak ligand. So how this is going to be helpful for us to identify the magnetic properties and color properties? Let me explain you from here itself. Here we can see that all the electrons are paired. That means there is no unpaired electrons. There is no unpaired electrons. So unpaired electrons is equal to 0 here. And so this is not going to give you color, because if unpaired electron is there only, it will give you color due to transition. Whereas here if you can see unpaired electrons are present. How many unpaired electrons are present now here? 1, 2, 3, 4. Unpaired electrons. 4 electrons are present. Due to this one, we can see the splitting. Due to this splitting, we can see very clearly the number of unpaired electrons varied. Right. As it is weak ligand, it is going to have unpaired electrons. At a strong ligand, in this particular case, is not going to have unpaired electrons. Point number 1. And what this type of complexes are going to be called? This type of complex is going to be called as low spin. What is the meaning of low spin? The electrons are entering into dx square by dxy, dyz, dzx first only. Even pairing occurs first only before entering into the higher energy, and it is called as low spin complexes. This type of complex are called as high spin complexes. Why? Because 1, 2, 3. After filling 3 electron, the 4th electron is entering here. The 5th electron is entering here. So before the pairing occurs, the electron is moving to the higher energy levels, then the pairing occurs, and so it is called as high spin. This high spin and low spin again we will discuss in the next lecture also separately, because high spin and low spin will be discussed much in detail based on spectrochemical series. Even here also is spectrochemical series only. Because of this spectrochemical series only, this cyanide ion is we are considering as strong complex, which is helping to form low spin complex. The water is weak, and so it is helping to form high spin complex. And here along with that, what else there are the applications of this particular strong field and weak field? Here we can see strong field, right? How many unpairs are there? 0 unpairs. So magnetic momentum. Already we know magnetic momentum will be considered based on unpaired electrons only. Of course, there is a formula to calculate for 3D group elements only. I am not writing 4D and 5D. There we have to consider L also. Here only I am considering spin quantum number. From that, it is going to be root of n into n plus 2 formula. Here we can see number of electrons, where n is equal to number of unpaired electrons. Based on this one, we can see how much magnetic moment is going to come. Here, what is the magnetic moment from this particular complex? Obviously, there is no unpaired electrons, 0. For first one. For second one, what is the magnetic moment here? Here we can see 1, 2, 3, 4. 4 unpaired electrons are there. That means root of 4 into 4 plus 2. What is the magnetic moment? Obviously 6 4s are 24 is approximately equal to 4.9. So in this way we can calculate magnetic moment also. So these are the applications of this octahedral CFT in octahedral complex. Now I am going to explain you the applications of CFT in tetrahedral complexes.